We have already seen in earlier lectures that the Brownian motion and the operator, that Laplacian operator associated with that, and we have also seen the Fehn-Macaque formula, etc. And we recall few things already we have seen, and few things which are immediate, but we have not discussed, but which gives the power of calculations, etc. So, these are the things we are going to discuss today, and also we are going to understand why do we need to study some other stochastic processes beyond Brownian motion. So, here assume that the W is a standard Brownian motion, as we do all the time. So, here W t greater or equals to 0. We have already seen in week 3 that probability that quadratic variation of W t is equal to t for all t positive, 0 or positive. Okay. So, the quadratic variation process is actually the identity function of time. Okay. So, this thing already we have seen, and there how did you compute that? For computing that, we have taken a sequence of partitions, and there we have taken the increments. So, we have added the square of the increments, and we use the theorem that quantity, the summation of square of increments, converges in probability to the quadratic variation function. Okay. So, that was the thing what we have used to compute this thing. Okay. However, the definition of quadratic variation of square integrable continuous martingale, which was introduced in week 2. Okay. So, that was done using the Dubmer decomposition, correct. If you have a square integrable continuous martingale M, then M square is the submartingale, and that M square has Dubmer's decomposition, and in the Dubmer decomposition, the non-martingale part, the part which is increasing part, so that constitutes the natural version of that constitutes to the quadratic variation of the process. So, that thing does not give you any indication how to compute quadratic variation, correct. So, that thing does not immediately suggest a way to find the expression of quadratic variation. Nevertheless, when we know the quadratic variation, I mean from this point on, so we have already obtained it of the Brownian motion, we can apply Ito's lemma to obtain the Dubmer decomposition. Okay. So, the Dubmer decomposition we can obtain. How do we do? We just take f of x is equal to x square, okay, this function. Okay. And then we apply f of w t, okay, apply Ito's formula on f of w t. So, f of w t is w t square. So, f of w t is equal to f of w 0, that is w 0 square, plus first order derivative of f, that is 2x. So, 2 times w s, okay, evaluated at w s, and dw s is running from 0 to t. Then Ito's formula also have second order term. So, plus half times 0 to t second derivative of f. So, what is second derivative? The 2x derivative is just 2, correct, 2, and then the quadratic variation would appear, or Brownian motion would appear. Okay. And this already you have computed that this can be taken as just t here, because this whole integration, okay, in this path, this is t, I mean, okay. So, I can write down s here. So, half and 2 would cancel each other. So, integration 0 to 2 of ds is t, okay, t, and here we have 2 w s ds. Okay. So, w t square is now written as some constant. So, w 0 is actually 0, because standard Brownian motion is 0, it is nothing is here, and here we have stochastic integration of 2 times Brownian motion with respect to Brownian motion. Okay. So, this stochastic integration gives me a local martingale, okay, and here this is the remaining term. Okay. So, this is also the Dubmer decomposition of w t square. Okay. So, this is obtained using the Ito's formula. Okay. So, after talking about Brownian motion, now we also so this is just it was formula of function of x, but function of x and t if we have. So, this is a special case. If f is twice continuously differentiable with all derivatives bounded, then Ito's lemma also implies, this is also a recollection of Ito's lemma, what we have already seen, that f of t w t is equal to f of 0 x 0. So, so here it should be w 0, okay. So, this is a typo, plus integration 0 to t first derivative of f with respect to first derivative of f, okay, with respect to the second variable. So, that is why I am writing x, that means the second variable. For first variable I would write t always. So, f x w s d w s 0 to t plus then first the derivative with respect to the first variable appears, and then here I mean there I should have written small s w s, this is missing here also, small s w s, the function of two variables, correct. So, this s s is missing here, d s, and then second order term that would give me half times double derivative of f with respect to the second variable, and then quadratic variation of w, that is ds. So, quadratic variation of Brownian motion is s, okay. So, that is the reason that this both we can club together, okay, we can club together, can write this manner. Okay. So, these are the things which is more or less recollection. But this is something we are going to use also for some interesting examples. So, here we now address the question that how can we find out quadratic variation of some other processes. For Brownian motion we have obtained, correct. The definition of quadratic variation did not help much, but we had to actually use the property of Brownian motion, that normal random variables etc., and then the fourth order moment of the normal random variable is 3 times of of the square of the variance etc. All these things we have used there. So, here indeed the following product table works for finding quadratic variation of another process whose infinitesimal change is or increment is retained using Brownian motion, okay. So, for that, so if I have a process x, so dxt is written in terms of Brownian motions, increments etc. So, dxt whole square I can then find out, okay, and then actually I would have product of terms which has infinitesimal increments, and then one should know that what are the what are the terms and how to manipulate those terms, okay. This is not very clear. However, this table really works, that whenever one has those type of products, so dt into dt one can put 0, dt and dwt one can put 0, and dwt into dwt one can put dt, okay. So, this product table really works for calculating quadratic variation of some other processes, okay. So, here we first talk about some process which is other than Brownian motion, say st, okay. We define st is equal to e to the power of alpha t plus beta times wt, okay, where alpha and beta are some constants, okay. So, this has a name, this is called geometric Brownian motion with drift, okay. Why geometric? Because there is no geometry after all, I mean it is just that product, because Brownian motion has additive increments etc. here, but it is in the power of e. So, like here I mean the product type of things do appear here. So, that is why we call it geometric Brownian motion. Okay. So, we are going to study this st, okay. So, we would like to write down this st, the infinitesimal increment of st in terms of infinitesimal increment of wt, okay. So, that is the kind of thing we want to do. So, one can actually directly apply Ito's formula over this, okay. It is a function of Brownian motion, correct. One can apply this Ito's formula, correct, and by applying Ito's formula one can get dst, correct, okay. So, that one can get, and one can get the formula, okay. So, that is one way to find out the change of dst etc., and then dst square one can find out, okay. There is another way, Okay. So, basically I am writing down what one would get. So, in general, so not with this alpha, this beta, but some other constant mu and sigma. Consider this type of description of a stochastic process, where increment of the process, stochastic process at time t dst is equal to mu, a constant, times st dt plus sigma st dwt. Okay. How are we going to understand this? We can understand this as a integral equation, correct, because say for example, the integration sign is there 0 to t etcetera, but that is just omitted, and then st is the unknown which appears both sides. Okay. So, one can understand that this description as an equation. Okay. So, we are going to see that how are you going to solve this equation and what are you going to do. But before that, let me explain that if dst has this form, then the quadratic version of st would be just you take dst's whole square, then you get mu st dt plus sigma st dwt whole square term, and then you use that product rule, that the table, and then you would see that dt square term would not appear, dt and dwt, that cross terms would also not appear, only this term would appear, and then there will be sigma st dwt whole square term would survive, that would give me sigma square st square dt. Okay. So, the quadratic variation of st would become integration of sigma square st square with respect to time t. Okay. So, that is the kind of thing. However, we need to build the connection between this and this. Without building this connection, the whole discussions is baseless, correct. So, we are going to build that connection. Okay. So, one connection, as I told that you use Ito's lemma on this and get it. Okay. So, that you can do as an exercise. Another, because there is nothing to do much, this is just a direct application, you would get it. I mean, one can see from here directly that one would get this type of terms, because the derivative of this would, you get partial derivative to x variable would get beta terms here, and same e to the power, so st dw is okay, and then for time here you get alpha terms, from here you would get half of beta square. Okay. So, you are going to get here. So, we are not bothering much in that direction, but the reverse direction. So, assume that I do not have that, I just have this thing. Okay. Then how to come up with that thing, okay? That solution. We can call then this thing as a solution of this equation. Okay. So, we proceed this way. So, for the time being, because we do not have any way to actually assert that this has a solution, for the time being we assume that the above equation has a continuous solution with probability 1. Okay. We assume that it has, and when we assume and then you obtain that form, and then we can do the reverse thing. We can actually use Ito's formula to cross verify that this is indeed the solution. Okay. So, assume that it has a continuous solution. I mean, this kind of treatment what I am doing now is very similar as you have done in your college, in your graduation level, when given an ODE, ordinary differential equation, you tried to find out the solution, try to find out the form of the solution, correct, without bothering much whether solution exists or not. Okay. You believe that it exists and then applied some formula to solve it, and this is actually a correct occasion to clarify the importance of Ito's lemma, because when you try to solve ordinary differential equation, what you actually have done is that you tried to integrate. Okay. You try to integrate. Okay. You try to apply the fundamental theorem of calculus that you wanted to see that as an antiderivative of some other function. But now, for stochastic calculus here, that fundamental theorem of calculus does not hold, because I mean in that form. So, what is substituting is the Ito's formula, because that actually helps shows that what is the correct thing to look at. Okay. So, Ito's formula is the thing what you are going to use for this. Okay. So, assuming that ST has a, I mean this has a solution, then we use exactly the way we used to think in for solving ODE, that since the unknown is multiplied here, so we are going to take log of these things. Okay. So, we do exactly the same manner. F of st we define, f of st is log of st, and then this is not defined when st is negative, correct. So, we can only define this for time t which is less than the exit time of the positive domain. Okay. So, the first time when st becomes negative, I mean non positive 0 or negative. Okay. So, exit of the upper half plane, okay, exit time of the upper half plane. So, for all t which is before the exit time, then it is well defined, then I can define it. Okay. So, after assuming that this equation has a solution, I am considering f of st and apply, and I am going to apply Ito's formula on this. Okay. So, here ds, the quadratic variation of st also I am calculating, as I have indicated earlier, that it will be sigma square st square dt. So, the increment of quadratic variation of s is sigma square st square dt. Okay. Now, I am since I know all these things, so I can apply now Ito's formula. You remember that for applying Ito's formula of a function of a process, I need quadratic variation of that process, correct. So far I just knew the quadratic variation of Brownian motion, okay, but using that product table I now write down this is the quadratic variation of st. Okay. So, we are going to now use the Ito's formula here. D log st is equal to, okay, now if Ito's formula, the derivative comes f prime st dst plus half times double derivative of f st and then the quadratic variation. So, quadratic variation is sigma square st square dt. Okay. This is just direct application of Ito's formula on this. So, now here we compute. So, f of st is log st. So, derivative is 1 over st therefore, and here double derivative is minus 1 over st square. Okay. So, that thing would come, but st square and this st square would cancel each other, but I would retain the negative sign. So, minus sigma square dt, half is also there, half is there. So, from this I am going to get this, and from here this dst I already know this is the form. So, I am going to write down dst is equal to mu st dt sigma st dwt. Okay. So, like here. Okay. Here this subscript t is missing, 1 over st sigma st dwt plus mu st dt. Now, here I have st and I have st here, and anyway my st's are positive. So, these things all make sense, we can cancel these st's etc. So, we get a very nice formula here. So, very nice thing. So, here I just have sigma dwt from this part, from this part I have mu, and from here minus half sigma square. So, mu minus half sigma square by 2 dt. So, that is the form. Okay. So, now I can integrate both sides from 0 to t. So, if you integrate this from 0 to t, I would get log st minus log is 0. That log is 0 I transfer to the right hand side. So, log of st is equal to log of s0 plus integration of this is very easy, just sigma times wt. Integration of this is just constant mu minus sigma square by 2 times t, and now I take exponential both sides. So, it is st is equal to s naught times e to the power of this term sigma wt plus mu minus sigma square by 2 t. Okay. But t is running from 0 to tau. Okay. I cannot assure that this is the expression for whole positive real line, because this thing is only makes sense when t is less than tau. Now, if I can prove that tau is infinity with probability 1, we would be done. So, we need to do that. Okay. We need to do this. So, it remains to show that probability that tau omega is finite is 0. Okay. So, we are going to show that tau omega finite, that event would happen with probability 0. So, now let omega be such that tau omega is finite. Okay. So, I would like to show that this class of omega is coming from 0 major set. Okay. Let omega be such that tau omega is finite and the solution exists for up to tau omega. So, I cannot say t is equal to up to tau omega. So, let t, now we are letting t tends to tau omega. Okay. We are going to take the limit. Okay. And then we are also going to use continuity of st. Okay. So, here we actually do not need to do much here. So, let us see what we do. So, here since st is a continuous path solution. So, tau omega is the time when st becomes 0 or negative, but before that it was positive. So, if it has a continuous path at tau omega, it should be 0, correct? It cannot be negative. Okay. So, here limit t approaches to tau omega, okay, of st, that is st omega minus. Okay. So, that is 0. Okay. So, now for this we know the expression of st, we are writing that and allowing this thing t is increasing tau omega. Since all these functions are continuous functions, because e to the exponential function, okay, these are all continuous function. So, as t tends to t tau omega, this converges to here for that each and every omega. So, s naught into e to the power of sigma w tau omega minus, okay, and also Brownian motion is continuous. So, actually I can write the tau omega also here. So, mu minus sigma square by 2 tau omega. So, this basically this goes to tau omega, the minus sign is not important here, is makes no sense, tau omega. Okay. So, here this tau omega. Okay. So, this is only, I mean same thing is written actually without minus sign. Okay. Now, this thing we have obtained, but we have assumed that tau omega is finite. So, e to the power of some quantity here, okay, some quantity which is almost surely Brownian motion for every omega you get a finite value, correct. Okay. So, here this is non-zero surely, because here this is just e to the power some number. So, that is that cannot be 0. So, we get a contradiction. So, what does it imply? So, this contradiction proves that, so for almost no path we can see that tau omega is finite. We have arrived at this contradiction by assuming that tau omega is finite, correct. So, then you have arrived at this contradiction. So, tau omega is obtained by the exit time of the solution. So, almost no solution paths are such that tau omega can be found finite, or in other words, when we are looking at solution, st is equal to s naught into e to the power of sigma w t plus mu minus sigma square by 2 t, okay, for all t positive. So, this is, see, I mean this is a geometric Brownian motion by definition, because here I have Brownian motion times some constant here, and here I have a drift term. Okay. So, geometric Brownian motion with drift. So, the definition when we have visited that are alpha and beta. So, this is alpha and this is beta. Okay, this is beta. Okay, good. Now, when one obtains this, one can say that okay, I have obtained this by assuming that it has a solution, but how can you be sure that it has actually a solution? But okay, now I have this formula. Okay. Now, from this you use Ito's formula on this function, okay, because this exists of course, because Brownian motion is there, okay, it is just a given, okay, and then we obtain that this solves that SD. It is very straightforward to check that this actually solves that SD. Okay. So, this gives you an idea that how one can solve a given SD. Okay. Just it is not very different from the things what you have done in your ODE course in undergrad level, but only thing is that the formula is different, and I mean here some kind of analysis which one has to be careful. One takes log function, correct. So, this is nothing other than that. Okay. Otherwise, it is not much difficult thing. Okay. So, next what we do is that we would check what is the utility of this process. Okay. So, this process is actually very popular for its application in modeling stock price market. Okay. And that is also a field which gives rise to some other processes for which one may not actually find out such kind of closed solution, correct. So, this is no solution in the closed form, and then for those applications it also becomes very important to actually develop a theory for stochastic differential equations. So, we call these equations as stochastic differential equation, because this is of course differential equation because some differentials are involved, but it is random, correct, because the Brownian motions are there. So, then it becomes important to develop a theory for stochastic differential equation that even one cannot find out, or one cannot solve the equation in known elementary, in terms of elementary functions, but still can one assure existence of the solution. Okay. So, that also becomes important. So, we are going to see those type of examples also. First, we just recall that what was the starting of the applications of stochastic processes. So, here the first mathematical model of market appears in PhD thesis of Louis Becquelier. So, it is some very old picture of Louis Becquelier. This appeared in 1900. So, more than a century before, correct, 120 years back. So, there he actually, when he used this, I mean he studied market using stochastic process. That time no mathematical tools for Brownian motion was existing. Okay. I mean the name of Brownian motion was also not common there. Okay. However, he used random walk, etc. Actually, he used random walk, and then actually he came up with correct formulation Brownian motion, okay, in his PhD thesis as a limit of random walks. Okay. This is actually 5 years before Einstein's paper on Brownian motion. Okay. So, the model however failed to capture the positivity of stock price. So, Brownian motion is anyway, I mean, can go negative. So, as a model it was pretty much useless for application. However, that was beginning of the effort that that using stochastic process or the tools in probability theory for modeling stock price. So, he modeled the stock price using Brownian motion in drift. Brownian motion was independently formulated by Albert Einstein in 1905, and then a long gap. Okay. So, the geometric Brownian motion, what we have just seen now, okay, with greater details, we have seen actually the SD for geometric Brownian motion, we have seen the definition of geometric Brownian motion, we have seen also how to derive the solution of the equation. So, this geometric Brownian motion was actually proposed by Paul Samuelson in 1965 to model stock price. Okay. So, it is nearly 65 years after the work of Louis Becquelier. So, Louis Becquelier tried to use just the Brownian motion, and then geometric Brownian motion was proposed by Paul Samuelson in 1965. Okay, I mean the long gap is mainly because the Louis Becquelier's work was mostly ignored because nobody thought that okay, that can be improvised. Okay, and also the required tools, mathematical tools were also vastly unpopular, okay, during this time period. So, the model could overcome the non-positivity dispute what Becquelier had, but then in 1973 paper, okay, actually this work was done by Black and Scholes a little early. So, but they published that in 1973 that they used this geometric Brownian motion to model stock price, and then did some stochastic analysis to find out price of options. Okay. But that is a different thing. What is option? We are not going to details of the definition of these derivatives of stock price, but that was the first breakthrough in this field, and then many researchers become interested to study stochastic process because that gives better insight of pricing of tradable assets. Okay. so which is very much a real life scenario. Okay, so in the work of Black-Scholes, okay, and also followed by Merton's work, so they have shown that option price satisfies a Cauchy problem, okay, with a parabolic PD. Okay, so that they have done. Okay,